Every time you load a website, fire off an email, or jump into an online game, there's this invisible, incredibly powerful engine making it all happen. It's called the transport layer. And honestly, it's the unsung hero of the internet. So today, we're going to pull back the curtain and see exactly how it works.
So, what is this thing, really? Well, the best way to think about it is like the internet's own specialized postal service. It's this middle layer that sits between the wild, chaotic network of the internet and the apps you use every single day. Its one and only job is to make sure that a message from an app on my computer gets to the right app on your computer safely and soundly. All right, so here's our game plan. First, we'll look at the problem this postal service is trying to solve. Then, we'll see how it delivers mail to the right digital address. After that, we'll meet our two main characters, TCP and UDP. And finally, we'll connect it all back to why this actually matters in your day-to-day life. Let's set the scene. The internet, at its very core, is a massive, decentralized, and, let's be honest, kind of chaotic network. Packets of data can get lost, they can show up out of order, anything can happen. So we desperately need a system to manage that chaos. And that leads to the big question, right? It's not just about getting data from one computer to another. How do you send a message from, say, your Chrome browser all the way to a specific web server and then get a whole web page back perfectly intact? How is that even possible? Well, the answer is the transport layer. It's the ultimate project manager. It handles that end-to-end communication. It does something called segmentation, which is just a fancy way of saying it chops up big files into smaller, numbered chunks, and it makes sure those chunks go to the right application. It even controls the flow of data to stop the network from getting totally overloaded. It brings order from chaos. Okay, so that makes sense, but how does it know where to send the data? I mean, your computer could be running a browser, a game, and a music app all at the same time. When new data arrives, how does it know which app to go to?
This is where it gets really clever. It uses something called a socket. Think of it like this. Your computer's IP address is its street address, but the port number, that's like the specific apartment number inside the building. A socket just combines the two to create a super precise address for an application. And this whole process, allowing all your apps to share the network at once, is called multiplexing. It's the magic that lets you browse, game, and stream all at the same time.
And what's cool is that a lot of these apartment numbers are standardized. For example, port 80 is basically the universal front door for any standard website. Port 443 is for secure websites, the ones with the little lock icon. Port 25 is for email. These standards make sure your data finds its way home, no matter where in the world it's going. All right, it's time to meet our first main character, TCP, the Transmission Control Protocol. When you absolutely, positively need every single piece of data to arrive in the right order with zero errors, think loading a web page or downloading a file, you use TCP. It is the registered mail of the internet. But how? How can it possibly guarantee that? Well, TCP doesn't just start yelling data into the void and hope for the best. Nope. First, it establishes a formal, verified connection using a really elegant process. And here it is. It's called the three-way handshake, and it's really just a simple, polite conversation. First, your computer sends a little packet called a SYN, which is like saying, "Hello, server, are you there?" The server replies with a SYN-ACK, which basically means, "Yep, I'm here. I hear you loud and clear. You ready?" And finally, your computer sends one last ACK, saying, "I'm ready." And only then, after everyone's on the same page, does the data start to flow. But the management doesn't stop there. Once the connection is live, TCP uses a technique called the sliding window to efficiently send multiple chunks of data at once. It also performs congestion control, automatically slowing down if it senses the network is getting jammed up. And, of course, if it sends a piece of data and doesn't get a confirmation back, it just sends it again. With TCP, nothing gets left behind. Now, what if you don't need that level of absolute certainty? What if the most important thing is just speed? Well, for that, we meet our second hero, UDP, the User Datagram Protocol. If TCP is registered mail, UDP is like a postcard. It's fast, simple, and gets straight to the point. UDP's whole philosophy is fire and forget. It completely skips the three-way handshake. It doesn't number the packets. It doesn't wait for any kind of acknowledgement. It just sends the data as fast as it possibly can. And the benefit?
It is incredibly lightweight with almost zero delay, which makes it absolutely perfect for anything happening in real time.
So this really boils it all down to the fundamental choice, doesn't it? With TCP, you get that guaranteed delivery, but it comes with some overhead. That's the extra time and data spent on the handshake and all the acknowledgments. With UDP, you get pure speed, but you run the risk of a packet or two getting lost along the way. It's all about picking the right tool for the right job.
Okay, so TCP, UDP, ports, handshakes, why does any of this matter to you? Because this choice, this trade-off between reliability and speed is quietly powering pretty much everything you do online. You use both of these protocols every single day, probably without even realizing it. Let's make this super concrete. Anything where the data has to be perfect uses TCP. When you load a website, you need every single pixel. A corrupted email is useless. But for real-time stuff, UDP is king. In a video call or an online game, who cares if a single frame of video gets dropped? Your eyes won't even notice. It's way better to drop a frame than to pause the entire stream just to wait for a retransmission. In those cases, speed is everything. And that really is the perfect way to sum it all up. The transport layer is that essential bridge. It takes the unpredictable, chaotic nature of the raw internet and transforms it into the orderly, reliable communication that our applications need to work their magic, whether that requires perfect accuracy or just pure, unadulterated speed. And that leaves us with a pretty fascinating question for the future, doesn't it? We live in a world that demands instant everything. Live streams, cloud gaming, AR, VR. As that hunger for real-time data just continues to explode, are we going to see a future where the raw speed of protocols like UDP becomes more important than TCP's perfect reliability? It's definitely something to think about.